All right, Lab 5, Magnetic Braking with Faraday. Introduction. We will collect observational data of a magnet falling through a conductive tube of aluminum foil, model that magnet tube interaction computationally, and compare computational predictions with our observed data. In this lab, we're going to use Faraday's law, we used Lenz's law, and we used the Biot-Savart law in our coding. Models. So we modeled the bar magnet and the aluminum tube computationally. Here's just a preview of our results. So experimentally, we found that the average time the magnet took to fall down the aluminum tube was 1.18 seconds. And when we did this computationally, we found it was 1.15 seconds. So very close. The experiment, so the system was the bar magnet and the aluminum tube. Surroundings was everything else. First thing we did was find the north end of the bar magnet. Then we dropped the magnet north end first down the aluminum foil. We did that 5 different times. And what you saw on the last slide was a little GIF of the experiment. Source of error, we might not have measured everything correctly when we were calculating the time, because we were just eyeballing it, going from frame to frame. So first try we got 1.1 seconds, second 1.26, third 1.13, fourth 1.23, and fifth 1.16 seconds. Then we just took the average. The data we used, so we had the length of our tube was 0.3 meters, the width was 0.006 meters, the inner radius was 0.02 meters, the mass of the magnet was 0.025 kilograms, and our mu was 0.9. So here's our code. This is, we had the base code, and then this is most of the stuff that we changed here. So here's where we put in the values to initialize some of our variables. We're doing that again with the bar magnet there. Here is us calculating B. And then in this function, we calculate the derivative of flux with respect to time here. This one is finding the F net. And here, I can't read it. Oh yeah, that's plotting the graph at the end. You'll see the results on the next slide. This one was our loop, and we're calculating the force, our magnetic force from the tube on the magnet. Then we also did this here, which is just updating our the velocity vector and the position vector of our bar magnet. So here's the output of our code. We got this nice little graph here. And you see the results. So the time it took was 1.15 seconds. So pretty close to our experimental. Our discussion. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The forces resisting the magnet would be stronger. They would be able to completely oppose the change in flux generated by the falling magnet, stopping it somewhere in the tube. Now, what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? The induced current would be lower, and then the magnet wouldn't, or it would fall through the tube even quicker because it wouldn't have that resistance.